Let's just do a little thought experiment. Imagine you have two absolutely perfect clocks. I mean, flawless. They'll never ever be off by even a nanosecond. So you line them up side by side and you start them at the exact same moment. For a little while, everything is just as you'd expect. Tick, tock, they're in perfect, beautiful sync. But now, you take one of those clocks and you send it on a journey. Doesn't matter if it's around the block or around the world. And then you bring it right back and set it next to its twin. What do you think you're gonna see? You'd think they'd still be perfectly matched, right? Note, against all common sense, they have fallen out of sync. They just don't show the same time anymore. And get this, it's not because one of them broke or the battery's dying. This is real. The clock that moved has literally experienced less time than the one that just sat there. So, what in the world is going on here? Well, the answer has a name: relativity. So, the first part of this whole puzzle is something called time dilation. The faster you move through space, the slower you move through time. And look, this isn't just some sci-fi theory. It's been proven. Scientists put these ridiculously precise atomic clocks on airplanes, flew them around the globe, and guess what? When they landed, those clocks were just a tiny bit behind the ones they left on the ground. Exactly what Einstein said would happen. But wait, there's more. Gravity does the exact same thing. The stronger the gravity you're in, the slower time takes for you. This is just wild when you think about it. It means a clock on Earth, stuck down here in our planet's gravity well, is literally ticking slower than a clock that's floating out in space. It even means that someone living on the top floor of a skyscraper is aging just a tiny, tiny fraction faster than someone on the ground floor. Now, you're probably thinking, okay, that's a cool little fact, but who cares? Well, you should, because this tiny, bizarre effect is absolutely essential for technology you use every single day. I'm talking about your GPS. Just think about how GPS works. You've got this whole network of satellites whizzing around, hundreds of miles above our heads. And way up there, so far from the Earth, the pull of gravity is a lot weaker than it is for us down here on the surface. And because of that weaker gravity, and also because they're moving so incredibly fast, the clocks on board those GPS satellites are actually running faster than our clocks are, right here on the ground. And we know exactly how much faster. It all adds up to a very specific and very crucial number: 38 microseconds every single day. GPS has to be insanely precise. It works by timing signals to the billionth of a second. So what would happen if the engineers just decided to ignore that tiny little 38 microsecond difference? Oh, it would be a total disaster. Your navigation would become completely useless. That tiny time difference would build up into an error of about 10 kilometers. That's over 6 miles every day. Your phone's map would tell you you're in the next town over. This is how real and how important relativity is. Which brings us right back to our two perfect clocks. Now we finally have the answer. It's impossible for them to stay synchronized. It's not about how good the clocks are, it's that the universe itself simply won't allow it. Space and time bend and stretch for every single one of us differently. There's just no such thing as a universal now. My now is different from your now. So what time is it really? Well, that all depends on where you are and how fast you're going.